Analysis and conclusion. Students should find the resulting equipotential pattern for the first configuration. That's where you had 2 point particles, and it looks like that's a little reverse from what we did. Over here it's the negative electrode, and here's the positive electrode. No matter, just the direction you hook them up. Notice how the data forms circular patterns. Why is it shaped like this? This pattern closely resembles the resulting equipotential lines from a positive and negative charge. The voltage at a point in space is dependent on the distance from each charge in the system, and that is a 1/r dependence. The closer electrode has a stronger influence due to this reliance on distance, and one electrode is much closer for all of the points, except of course right in the middle. Closer to the center of the page, the influence from the farther electrode increases and the pattern begins to straighten out a bit. You move away from the circular pattern. Finally, in the center, the pattern flattens out totally as each electrode exerts the same influence since the points on this line are equidistant from each electrode. For this configuration, the electric field, so we've switched from equipotential lines to electric field, is strongest close to the electrodes since the equipotential lines are closer together. The central equipotential line near the 6-volt mark shows the area where the electric field is the weakest, as the equipotential lines are furthest apart. Now the second configuration, unless you did this first, then it would be the first configuration. This is where you simulated 2 parallel planes by having your 2 lines of conductive ink and your tacks right here for where you connected up the power source. This resulting equipotential line pattern closely resembles uniform electric field. We expected that since the equipotential lines are equally spaced at the same voltage intervals. And here they are. And then you can see outside the planes, okay, so here's our conducting paint that simulated one plane. You start getting these edge effects when you get beyond the plane. If we were to place a charge on any equipotential line, it would require 0 work to move it along that line. All points on an equipotential line have the same electric potential, and that comes from this right here. The work to move a charge is your change in potential energy, which is equal to Q times delta V. So if I have 0 change in electric potential, I have 0 work. Therefore, no work is required to move a charge along an equipotential line. Where will a charged particle move when placed in an electric field? Towards a higher or lower electric potential? Which way? Well, it depends on the polarity of the charge. The electric field direction is defined as the direction a positive charge accelerates. The electric field points from high electric potential to low electric potential. So a positive charge will move from high to low electric potential. Opposite is true for an electron or any negative charge. An electron free to move will accelerate opposite the direction of the electric field. Therefore, the electron moves from a low electric potential to a high electric potential.